Hello, I welcome you all in this course on mechanical measurement systems. Today we will discuss the piezoelectric transducers, and discussion will focus only on piezoelectric transducers. Now, piezoelectric effect is the effect when a substance is compressed or expanded or compressed, and the force is exerted. For compression, the force is exerted and some strain volumetric deformation in the substance takes place. Due to this volumetric deformation, when the opposite faces are charged, this is known as piezoelectric effect. So, either we charge opposite faces and deformation takes place, or we deform the substance and charging of opposite face, vice versa. Right? Now, we can have relation between the charge developed here and here, it is sort of capacitance, right, and with the displacement, function of displacement. This is the basic working of the piezoelectric transducer, and this property of transducers is for many uses. I mean, not only it is used as a sensor, even in wristwatches also there is a piezoelectric transducer. Even in the pressure gauges for pressure measurement there are piezoelectric transducers. So, they have variety of applications like strain gauges. Now, for example, let us take example of a strain gauge. Suppose there is a flow in a channel, right? And if we insert a vertical with strain gauge fixed, and this is a flexible type of thing. So, this fluid will push this cantilever in this direction and strain will be developed. So, not only strain gauge can be used for measurement of the strain, it can be used for the measurement flow as well. Similarly, here for piezoelectric transducer, not only they are used as a sensor for measuring the force or the strain, they can have variety of applications, right? Quartz is essentially a piezoelectric substance. Quartz is silicon dioxide. This is quartz. Okay, it is available in nature in abundance. Now, every piezoelectric crystal, let us talk in terms of crystal, has three axes, right? One is x-axis, which is called electrical axis. Another is y-axis, which is called mechanical axis. And there is a z-axis, which is known as optical axis. So, suppose this is x-axis, this is y-axis, and opposite to the board it is z-axis, right? And there are two effects in transducers. One is longitudinal effect. In longitudinal effect, suppose this is x direction and force is applied here and deformation takes place. The charge will be developed here on the opposite faces of the crystal, and this is known as a longitudinal effect, and it is independent of the area. It is not dependent upon the area and thickness of the crystal in this direction, x direction, right? It is mainly dependent on the force applied on the crystal, right? So, this is the longitudinal effect. Another is transfer effect. In the transfer effect, where the force is applied in this direction, either of the direction, I mean either from this direction or from this direction. Definitely this from here we will getting the reaction force, and then charge is developed in the opposite phases. This is known as longitudinal effect, and it is dependent upon the x and y direction of the length. So there are two effects in transducers. One is longitudinal effect, another is transverse effect. Right? Now, if you look at the arrangement of the silicon crystal, arrangement is like this. There is the hexagonal arrangement of atoms. This is silicon, and smaller one, let us say oxide, and hexagon is the prism, hexagonal arrangement, and on the bottom side also 3 more oxygens are attached to it. So it is a structure of a crystal. It is not atomic structure, it is a structure of a crystal of silicon, right? Now, if length and L and B are the length and breadth of the surfaces, right? In that case, the capacitance, because the opposite phases charge is developed. So some charge is developed because it will work as a capacitor. So capacitance is Cx is equal to epsilon A by T. T is the thickness of the crystal. And this epsilon is permittivity, and epsilon is relative permittivity multiplied by absolute permittivity. Or we can write as epsilon R, epsilon O, A by T. Okay. Now voltage, because charge is difficult to measure, but once we can easily measure the voltage across 2 phases, it is easier to measure. So V is equal to Qx by Cx, right? And it is equal to D11 Fx by Cx. Now there is a parameter which is D11 has come to the picture. This is discharge coefficient. It is unique for every material, for a particular crystal. D is coefficient of discharge sensitivity. D is coefficient of discharge sensitivity. Now it has 2 subscripts, 1, 1. 1, 1 means first subscript is electrical effect and second subscript is mechanical effect. It means if force X, it is x-axis. So force and charging are on the same axis, right? So it is charging effect and force effect. So first subscript direction of electrical effect and second for mechanical effect. So mechanical effect and electrical effect are on the same axis. If it is D12, it means electrical effect in this axis, mechanical effect is in this axis. Suppose we charge the crystal in like positive and negative, the D12 will indicate the mechanical effect of charge in this axis. It will swell or it will shrink. So here we are taking D11. It is coefficient of discharge sensitivity. Now once we have coefficient of discharge sensitivity, Vx can be written as D11 sigma T divided by epsilon naught epsilon r. Now this is Vx across x. Is it clear? Because sigma is F by A. So this epsilon A, this F is divided by A, that is how we are getting sigma xx. And T is already there, right? Now, it can be replaced by G11 sigma xxt. Now, there is another term, G11. So, G11 is, G is voltage sensitivity. It is voltage sensitivity, and G11 is equal to Vx by sigma xxt, right? And we are concerned with voltage sensitivity, right? Now, for force in y direction, suppose now we have taken force and electric axis and mechanical is same. We have taken D11. Now, in the second case, when force is applied in y-axis, charging will be there in the x-axis, force is applied on the y-axis. When the force is applied on the y-axis, then Qx is equal to D12y, sorry, Fy. Fy. Or D12A sigma y. Because stress is replaced by sigma, sorry, the force is replaced by stress multiplied by the area. Now, Cx is again epsilon naught epsilon r A by T. This is a formula for Cx. Now, Vx is equal to again Qx by Cx, and again D12 A sigma y T by epsilon naught epsilon r divided by A, then A and A will be cancelled out, and it will be D12 sigma y T divided by epsilon naught epsilon r. That's it. Now, from here we can find the value of G12. Now, G12 is equal to Vx by T divided by sigma y and is equal to D12 divided by epsilon naught epsilon r. Right? Now, we'll go in the next step, we'll go for the first order response, because it is a first order system. So, if we want to have response of piezoelectric crystal, because it is known for a very quick response, piezoelectric crystal is known for a very quick response. So, we'll do the first order analysis of piezoelectric crystals. Now, Q is equal to KQX, where KQ is C by D. This is the charge C by per centimeter. Q is the charge, right? And in a piezoelectric system, it is not only crystal. Now, the crystal is connected to a charge amplifier, a high impedance amplifier. A crystal is also having a high impedance, and the cables which are connecting, if the cable is quite long, then it will also have certain order of or substantial C or capacitance in it. So, it is a, I mean, if we want to finalize a circuit for a piezoelectric transducer, it is going to be like this. This is current in crystal, and then it is a RC circuit, R and C. Because there is a capacitance in the cables, and then it goes to the amplifier, and amplifier is also I mean high impedance amplifier, not for the एक मिनट. Okay, say amplifier is a high impedance amplifier. Impedance of this is also is high, capacitance is there. So we will take current, suppose this is crystal current ICR. So ICR will be divided in two parts. One part will be going into this, another part will be going to, so this ICR is equal to IC plus IR, right? So part of the current is going to the capacitance and part of the current is going to the resistance. Now ICR is equal to dq by dt, this q, because this is a charge which is developed on the crystal. So this dq by dt is nothing but kq dx by dt. Or current is a function of rate of change of the displacement, dx by dt. Now here we have EMF which is same, this is EO, which is same across three, this one and C and R. So EO is equal to EC. Let us take voltage drop across the capacitance. This is equal to integral of IC DC divided by C. Because Q is equal to CV. It has come from Q is equal to CV. So if you want to have V, then Q is divided by C, and Q is integral of IC, sorry, not DC, it is DT, IC DT divided by C. Now this IC DT can further be replaced by EO is equal to IC is ICR minus IR, ICR minus IR multiplied by dt, oh sorry, IR dt divided by C. IC minus IR dt divided by C. Now we can say that CEO is equal to integral of ICR minus IR dt. Now if we differentiate this CEO, C E DEO by dt is equal to ICR minus IR, right? ICR is KQ dxi by dt. This is input displacement dxi minus IR. IR is again EO by R. Now we are formulating the first order equation. Now this is going to be C dEO by dt. Now we multiply this by R and we will take this to this side, then CR dEO by dt plus EO is equal to KQ R dxi by dt. Now this CR or RC, so we can write this as a lambda d plus 1 EO is equal to KQ R dxi, right? And if you want to have solution for this, then QO by QI, output by input, output by input is going to be क्या होगा, K lambda D divided by lambda D plus 1, where lambda is RC and K and static sensitivity K. K is equal to KQ by C. Because okay, this is because lambda is there, so lambda is replaced by C R by C. Okay, so KQ lambda is KQ lambda, static sensitivity KQ lambda, K lambda. Now K lambda is replaced by R by C, and we are getting this. Now here, if you want to have frequency response, because not only we require this transient response, we need the frequency response also. So for the frequency response of the first order system, in this case is going to be QO by QI omega lambda whole square divided by 1 plus omega lambda whole square. This is going to be the frequency response of this piezoelectric crystal or piezoelectric material. So in a piezoelectric crystal, first of all, the charge sensitivity D and permittivity this or epsilon naught R, whatever you want to take, epsilon naught R, okay, they are not affected by temperature. They are not affected by the temperature. Tourmaline is the only material that exhibit large sensitivity in volume expansion mode in Z-axis, and its useful temperature is up to 1000 degrees centigrade. There is a crystal made of Rochelle salt. There is another piezoelectric material which is largely produced for, in old days it was used as a pressure pick or pickup for, not pressure pickup for the gramophones. Nowadays for silicon microphones, this salt is being used, and there are number of materials, piezoelectric materials. We can have piezoelectric material like barium titanate that can also be made a piezoelectric, it has very good piezoelectric response. But if you take the quartz crystal, quartz is quite reliable, and if you want to make temperature measurement, for the measurement of the temperature it is quite reliable. And for suppose, because temperature measurement in piezoelectric crystal is done with the frequency response, right? For example, this is the fundamental frequency of a piezoelectric crystal. This is 1 plus alpha t plus beta t square and so on. But if we take the quartz, right? If we take the quartz, it is highly linear in a range of 193 Kelvin to 573 Kelvin, or 193 Kelvin minus 80 degrees centigrade to 300 degrees centigrade. So quartz crystal is quite linear, and change in the frequency is rated with the temperature in the case of quartz crystal. And say if I said linear, then it is going to be right. Fundamental frequency, F is the fundamental frequency. T is the temperature. T is the temperature in degree centigrade. It is not in Kelvin. Though it is capital T, I have written capital T, but it is the temperature in degree centigrade. And the alpha, the value of alpha for quartz is 35.4 into 10 to power minus 6 per degree centigrade. That is the value of alpha for quartz. Now, for 1 degree centigrade temperature, suppose I want to change temperature by 1 degree centigrade. Fundamental frequency is 28.2 megahertz. That is FO. So fundamental frequency is 28.2 megahertz multiplied by 1 plus alpha t. So one plus alpha t, okay. Because there is a change in the temperature, we are saying the change in the temperature is 1 degree centigrade. So the difference change in the frequency or the change in the frequency is going to be multiplied by 35.4 into 10 to power minus 6. And this is also 28.2 megahertz, so it is 10 to power 6. Now I am repeating, frequency at a particular temperature is fundamental frequency plus 1 plus alpha t, where t is in degree centigrade. Now suppose there is a change in temperature by 1 degree centigrade. The moment the temperature changes 1 degree centigrade, it becomes FO plus alpha FO, right, for 1 degree centigrade temperature. Now if you take the difference, then the difference is going to be the alpha FO, right. So this is basic frequency 28.2 megahertz. If we have converted into the hertz, 35.4 is the value of alpha into 10 to power minus 6. If we take multiplication of these two, 28.2 and 35.4, it is 998.28. Approximately it is 998.28, or approximately it is 1000 hertz. So in a piezoelectric crystal is a silicon or the silicon oxide or quartz crystal, if there is a change in the 1 degree centigrade temperature, the change in the frequency is 1000 hertz. Or if we take a 5 digital display, it can read the accuracy of measurement as 0.001. So with the help of a quartz crystal, we can have the temperature measurement up to the order of, because the frequencies, change in the frequency is 1000 hertz, right. So we can go up to the temperature measurement or accuracy in the measurement up to 0.001 degree centigrade. So that is the benefit of the quartz crystal. We can go for a very high accuracy or temperature measurement of temperature measurement. In addition to that, there are many applications for these crystals, not only in the area of instrumentation measurement. In physical systems also, many places the quartz, this property of quartz is used, especially for actuation in the wristwatch, or actuation in many of the mini or micro machines. Now the quartz crystal is minus 40 to 250 degree centigrade temperature. The measurement, the deviation from the linearity is 0.05 degree centigrade. So it is quite linear as far as the temperature measurement is concerned, and the quartz crystal is placed, it does not come into the direct contact with the measurement. It is put in a capsule or a cylinder of copper, and this cylinder is again put in a tube of stainless steel, and this stainless steel tube surface comes into the picture of the measurement. If now we can have bank of piezoelectric materials also. If we put two piezoelectric materials or two piezoelectric wafers in series, right, then they become bimorphs. Bimorphs, there is one thing, bimorphs, and another is multimorphs. Bimorph means there are two slices of crystal, and they are put side by side. Mechanically they are in series, okay, and they are of two different piezoelectric material. They can be connected in mechanically also, they can be, I mean, electrically also they can be connected in series, or they can be connected in, this is connected in series, or they can be connected in parallel. Then this is series connection, and they can be connected in series, and they can be connected in, this is positive, so this is one terminal and this is another terminal. So this is negative, this is positive. This is how they are connected in parallel. So this is a parallel arrangement. Mechanically they are one by one, right? One over other. And so, but they can have parallel connection also, and they can have series connection also. Multimorphs, there are number of piezoelectric crystals. They are laid side by side, and these crystals are connected in parallel. So they all, this is plus, plus minus, plus minus, plus minus. So all plus are connected at one place, and all negative terminals are connected at one place. So this is the arrangement of biforms and bimorphs and multimorphs in piezoelectric crystals. That is all for today. Thank you very much.